This is how we graph the basic trigonometric functions, starting with the sine graph, which you could consider the mother of all sinusoidal graphs. And that's how you end up afterwards with a graph that looks like this, where it's got this wavy thing that keeps going up and down. And most people look at this and think, does not compute. All our lives we've been dealing with straight lines and lines that keep going in one direction. This one keeps coming back and goes through what we call a cycle because it repeats itself. Here's how it works. If we start with our basic x and y axes, I have labeled the positive side of the x-axis here in red because it is our starting point. We think about angles. Think back to the old-fashioned clocks, and I'm not talking about the digital thing that you've got on your iPhone that shows you the actual numbers. I'm talking about the old-school clocks like this. Now, we always think about starting at the 12 o'clock position and the arms swing around in a circle. They always go back to where they started. Think about that cycle because we're going to come back to it. Except I want you to think about a clock with one arm. In fact, that's how clocks started in the Middle Ages. They only had the hour hand. So just think about one arm starting at the 12 o'clock position. Every 12 hours it does a cycle and starts again. Now, our starting point, I'm going to turn the clock sideways so that the 12 o'clock position is now lying down. This corresponds to our starting position on the red line here. So we now have a 0 starting position here, 0 degrees. If we start here, we have 0 degrees because the angle formed by my marker against our starting point is 0. As it goes to 45 degrees, we get a different triangle which might look something like this. Here's our arm, here's our imaginary line, and there's our right angle triangle. So if we take, for example, the sine of theta, which is a sine of 45, we get a certain value. If we go up to 90, if we extend up this way, we head towards a different value and sine keeps changing. So in the case of sine equals 45 degrees, we could keep going around this way so that our angle of theta has now become greater than 90 degrees. At that point, if we drop our line to our horizontal, we have our 90-degree triangle there again, and the sine of this angle here corresponds to the sine of this angle here, which I'll call theta prime, because it's basically the original triangle just flipped over. But notice what happens. We have sine of theta, which of course is opposite over hypotenuse. This is a positive value because we're going up the y-axis. Hypotenuse is also always positive, and in fact, you see what happened here is like the arms of a clock, we are going on a circle like this. By the time we get down here, our angle is now gone past 180 degrees, and we now have another imaginary triangle like this. Right angle, so opposite over hypotenuse, but opposite is now going into negative territory because we're going down on the negative side on the y. So we have a negative value. Sine of this angle here is now some negative value, whatever this is here. Let us call this negative y because we're measuring it down on the y. And our fixed hypotenuse, which is still a positive value. Now, sine is going to be a negative value. Negative divided by positive equals a negative value. If we keep going around in this fashion here, we could, for example, starting again with my clock and getting rid of all this extra noise here, we could, for example, take our starting point. So, 0 degrees, and if I turn the clock sideways like this, a little bit of an angle so you can see, as we increase the angle, so the angle between the horizontal starting point and the arm that moves up here, we could take that, and as we see the end of the marker go around, it's going to form a spiral. So here we have 0 degrees, here we bring it up to 45 degrees, here we bring it up to 90 degrees. How does this look in action? If we do that, as you can see on the little animation to my left, we have the arm of a clock that's going around in a spiral, and it describes an angle that goes through all 360 degrees, forms a cycle, and comes back. As we take that angle and project it, we start to get something that looks like this. From our 90 degrees to up to 180, 270, which is 3/4 of a circle, and back to 360, which is essentially the equivalent of 0 degrees, and it repeats, we end up with this kind of graph. If we go backwards, we end up with the same thing, and so on, and so forth. That is how we arrive at what is called a cyclical, or in this case, because it's based on sine, a sinusoidal function.